Imagine a scenario for a second, right? A highly sophisticated threat actor just managed to, well, steal your company's master administrator passwords.
Oh, the worst case scenario. Yeah.
Right. I mean, they basically have the absolute keys to the digital kingdom. They can encrypt the databases. They can wipe the virtual machines. They can literally cause millions of dollars in damage.
Mm-hmm.
But, and this is the crazy part, they still cannot touch your most critical backup data. Why? Because the physical, actual cable connecting their network to your recovery vault, well, it literally does not exist at that moment.
Right. It's not there.
Exactly. So today, for you listening, we are driving into the engineering behind these kinds of impossible defenses, planetary scale infrastructure, and, instantaneous disaster recovery.
Yeah, it's really the absolute bleeding edge of modern enterprise IT architecture, designing systems that don't just perform well, but can actively survive catastrophic failures and malicious attacks.
Exactly. And to unpack all of this, we are exploring a highly specific, densely packed document. It's a practice exam for the HPE7-V01 certification.
Yeah, and it's a beast of an exam.
It really is. Now, to truly respect the engineering weight of these concepts, we are taking a deliberate, measured approach today.
Right.
No rushing. We are going to examine exactly 10 architectural scenarios in strict sequential order.
Because these scenarios, they really build on each other. If
Yeah.
you understand the mechanics behind these 10 specific problems, you basically understand the blueprint of a modern data center.
Totally. So here is how we'll break this down. For each scenario, I will explicitly announce the question number and then read the architectural prompt completely verbatim from our source document. Okay. And my guide here will then explicitly state the correct answer. Then we're going to look under the hood to understand the business impact, the failure states, and the exact why behind the technology.
Sounds like a plan.
Let's get right into the foundation. Question 1. A customer wants to scale out their newly acquired enterprise storage platform for block workloads. Which architectural principle applies when adding new controller nodes to increase performance?
The correct answer is A.
Okay, let's unpack this. We are adding more controllers to get more processing power, right?
Mm-hmm.
But what is the fundamental architectural principle at play here?
So the principle relies entirely on the back-end fabric.
Okay.
When you add new controller nodes, you absolutely increase your processing power and your front-end connectivity to the network. But, and this is the critical mechanism, all these nodes remain interconnected through a high-speed back-end fabric.
Ah, I see.
Yeah, this allows every single controller to access the exact same shared storage enclosures. It basically distributes the workload beautifully without creating isolated storage silos.
So if I can visualize this, is this essentially like adding more toll booths? Like the booths represent our new controller nodes to a massively congested highway?
Yeah, that's a good way to look at it.
Right. You add the booths to process cars faster. But you have to maintain a massive multi-lane road behind those booths, which is the back-end fabric, so that every single car, regardless of which booth it went through, can still park in the exact same giant parking lot, which is the shared storage.
Yes, exactly. And to build on that toll booth analogy, imagine what happens if you don't have that multi-lane road behind them.
It'd be a nightmare.
It would. If you just bolt on a new controller and directly attach a bunch of disks to it, you've created a silo.
Right.
If an application needs more storage space, but its specific controller's disks are full, it's just out of luck, even if the controller right next to it has like terabytes of empty space.
Oh, wow. Okay.
So the back-end fabric prevents that fragmentation.
Mm-hmm.
It ensures that while you have multiple brains processing the I/O, they all share one unified pool of physical resources.
That prevents stranded capacity, which is, a huge money saver.
Mm.
But getting the storage back-end right is really only half the battle, because all that storage performance is completely wasted if the network connecting those arrays to your application servers becomes a massive choke point.
Oh, absolutely.
And that brings us directly to the network edge. Question 2. You are designing a modern data center network using distributed services switches to improve application performance. What is the primary operational advantage of utilizing these specific switches at the top of the rack?
The correct answer is B.
So what is the source material telling us about the actual operational advantage here?
Well, it all comes down to hardware offloading. Distributed services switches offload critical infrastructure services like stateful firewalling, microsegmentation, telemetry, and, complex encryption away from the host server's CPUs.
Okay, so it takes the burden off the server.
Exactly. Those tasks are shifted directly onto dedicated switch hardware, which preserves the host server's resources purely for running the actual application workloads.
Wait, I have to push back on the physics of this for a second.
Okay.
If we are taking incredibly compute-intensive tasks like line rate encryption and deep packet inspection firewalls, and we shove all of that onto a top-of-rack network switch, doesn't that completely overwhelm the network here?
It sounds like it would, right?
Yeah, I mean, a standard switch processor just can't handle that kind of load.
Well, what's fascinating here is that you are completely right about a standard switch, but these are distributed services switches.
Wow.
They are built with highly specialized silicon. They're often called data processing units, or DPUs. They aren't relying on generic processors at all.
But they're custom built for this.
Exactly. They have hardware built at the microscopic level, specifically designed to encrypt data and enforce firewall rules at massive speeds without breaking a sweat.
So the business impact is that if I buy, an expensive server with high-end processors to run my critical databases, I am actually getting to use all of that processing power for the database.
Yes.
Instead of burning like 30% of it just to encrypt the network traffic.
Precisely. You basically stop using your expensive general-purpose application servers to do the mundane plumbing of network security.
Makes total sense. But speaking of network security, offloading firewalls at the rack level is great for everyday traffic. Standard network security policies will not save you, though, when a state-sponsored ransomware gang bypasses your perimeter entirely.
No, they absolutely will not.
So let's look at disaster-level defenses. Question 3. A financial institution requires a solution to protect against severe ransomware attacks using an isolated recovery vault. Which architectural requirement is fundamental to ensuring the recovery data remains completely isolated and untouched?
The correct answer is C.
Walk us through the mechanics of this vault. I mean, how is it different from just a standard secure backup?
The absolute fundamental requirement here is physical active network severance.
Physical severance.
Okay.
Yes.
The vault must maintain an absolute air gap from the production environment. The network pathway is physically disconnected. It is only open temporarily during strictly scheduled, tightly controlled data synchronization windows, and the moment the new backup data is pulled across, the connection is instantly severed again.
Here's where it gets really interesting to me. This isn't just a strict software firewall rule saying block all traffic. It functions more like a digital medieval drawbridge.
That is the perfect way to conceptualize it, yes.
Right, because the castle's bridge isn't just locked with a heavy gate. It is actively pulled up and physically disconnected from the mainland for like 99% of the day.
Right.
So if a massive ransomware infection completely takes over the production environment, the hackers can't just brute force the gate. The physical bridge to the backup vault literally does not exist.
And this solves the most terrifying problem in modern cybersecurity, which is compromised master credentials.
Yeah, that's the nightmare.
If a threat actor steals your highest level domain admin passwords, a software firewall won't stop them because they just log in and turn the firewall off. But if the network interface on the vault is physically down, all the stolen passwords in the world are completely useless. The vault only lowers the drawbridge on its own internal clock, pulls the data in, and then vanishes from the network again.
That is incredible. But, securing one highly guarded vault is relatively straightforward, taking those strict operational standards and applying them to a massive geographically scattered footprint.
Oh, that's a whole different beast.
Yeah, that introduces an entirely new kind of engineering chaos. Which brings us to question 4. A global enterprise manages thousands of servers across multiple edge locations and wants to unify their firmware compliance using a cloud-based management approach. How does the solution handle baseline deviations across different regional groups?
The correct answer is D.
So break down how this platform actually manages the deviations in the real world.
According to the material, this cloud-based approach allows IT administrators to define distinct compliance policies and assign them to specific localized server groups.
Okay, so it's not just one big rule for everyone.
Right. The cloud platform constantly monitors the entire global fleet to identify any servers that deviate from their assigned baseline. But critically, it coordinates the automated remediation, the actual patching and rebooting, only during the locally approved maintenance window for that specific location.
So what does this actually mean for the global IT team?
Hmm.
Why not just have one massive global policy that patches everything at the exact same time?
Yeah.
Doesn't having distinct local policies just create chaos?
If we connect this to the bigger picture, a monolithic global policy is actually a recipe for operational disaster.
Really? How so?
Well, imagine forcing a mandatory firmware patch globally on a Tuesday at 2 a.m. Eastern Time.
Okay.
That might be the perfect maintenance window for your servers in New York.
Yeah.
But 2 a.m. in New York is 3 p.m. in Tokyo.
Oh, right.
You would be ripping critical servers offline right in the middle of their busiest workday.
Oh, wow. That makes total sense. You'd be causing your own self-inflicted outage.
Exactly. This solution utilizes a unified, cloud-based baseline to centrally monitor everything. You know exactly who is out of compliance, but the execution is decentralized.
Got it.
The platform respects the local maintenance windows, which prevents business disruption while still maintaining global security standards.
That's brilliant. All right. We are moving from managing automated infrastructure updates to managing the humans who use that infrastructure, specifically developers and their budgets.
Right.
Question 5. An organization is deploying a hybrid cloud automation platform to provide self-service provisioning for their developers. How does the platform enforce budget control when developers request resources across various public and private cloud providers?
The correct answer is A.
What is the specific mechanism enforcing this control?
The automation platform integrates governance policy engine.
Governance policy engines. Okay.
When a developer requests to spin up new cloud resources, this engine evaluates the request in real time against current pricing, predefined budget limits, and tiered approval requirements.
So it's checking the math before it builds anything.
Exactly. If the cost of the requested resources pushes the developer over their established threshold, the provisioning process doesn't just fail, it is automatically paused. It sits in a pending state until an authorized manager explicitly approves the expected cost.
You know, this sounds exactly like giving your engineering team a corporate credit card.
The underlying logic is identical, yeah.
Because the card empowers them.
Yeah.
It works automatically, letting them buy the cloud resources they need to iterate quickly without submitting an IT ticket for every single virtual machine.
Right, which slows everything down.
But the moment a developer tries to spin up a massive AI cluster that crosses their, say, $5,000 monthly limit, the card instantly freezes at the digital register. It flags a manager for an override.
And that circuit breaker is vital. I mean, in the era of public cloud, infrastructure is essentially infinite, which means your potential bill is infinite.
Oh, yeah.
We have all heard the horror stories of a developer accidentally writing a looping script on a Friday afternoon and the company waking up on Monday to a $100,000 cloud bill.
Yep. The infinite loop of doom.
Exactly. The governance policy engine completely eliminates that risk.
Awesome. Now, when developers are provisioning all these new workloads, the business must ensure they are properly protected in case of a disaster, which is our next topic. Question 6. When designing a disaster recovery architecture based on continuous data protection, the architect must properly size the recovery journal. Which primary factor dictates the required storage capacity for this journal component?
The correct answer is B.
Let's explore the math behind disaster recovery sizing. It can be tricky.
It can. In a continuous data protection or CDP architecture, the recovery journal is responsible for storing every single ongoing change made to the workloads over time.
Every single change.
Right. Because of this, the required storage capacity is not based on the total size of the servers. It is primarily determined by the workload's expected rate of data modification, which is the change rate, multiplied by the desired time frame the customer wants to be able to rewind, plus some standard overhead.
I think a lot of people get tripped up on this concept. So if I have a massive application environment, let's say 100 terabytes of virtual machines, my recovery journal is not sized to hold 100 terabytes.
This raises an important point about the difference between a baseline sync and a continuous journal.
Okay, lay it out for us.
You do have an initial baseline copy of that 100 terabytes, yes. But the journal itself, it only holds the delta, the exact blocks of data that have changed.
So if my 100 terabyte environment is mostly static and only 1% of the data actually changes every day,
then your daily change rate is just 1 terabyte.
Oh.
If your business requirement is to be able to rewind time to any second within the past 5 days, your journal only needs to hold 5 terabytes of data.
Wow, that is a huge difference.
It is. If you had to continuously store the entire 100 terabyte baseline over and over again, the storage cost would bankrupt the company. Focusing purely on the modified data makes CDP highly efficient.
Makes sense. Properly sizing that capacity is crucial. But precisely measuring exactly how much capacity is being used is just as critical, especially when the business is paying for storage as a monthly service. Let's examine how the billing mechanics work. Question 7. A customer is reviewing their newly implemented capacity as a service model for their primary storage arrays. How does the metering logic differentiate the billing metrics for a highly virtualized database environment?
The correct answer is C.
So what is the metering logic actually looking at here?
The core function of the metering system is to measure the actual physical written data capacity on the storage arrays themselves.
Just the physical data.
Yes, it intentionally ignores how much space the hypervisor has then provisioned to the virtual machines. The service meters only the capacity physically consumed on the storage media, ensuring the customer is billed strictly for true consumption.
Thin provisioning can be a bit of a logical illusion to wrap your head around. Let's try an analogy for this one. Is this basically like me signing a lease for a massive, completely empty virtual warehouse?
Go on.
My virtualization software tells the server operating system, hey, congratulations, you have 1 million square feet of warehouse space available to you.
Right.
That is the thin provisioning. The OS thinks it's huge. But the capacity as a service metering logic completely ignores the hypervisor's claims. Instead, the billing system walks into the warehouse and only measures the square footage of the actual physical boxes I have placed on the floor. It completely ignores all the empty promised space.
That captures the dynamic perfectly.
Okay, good.
The hypervisor has to lie to the operating system and pretend the space is massive so the databases don't panic and crash. But you should never pay for a logical lie. True consumption-based billing looks past the thin provisioning and meters the physical footprint of the written data.
Love that. Never pay for a logical lie. Okay, beyond single-site capacity, modern enterprises cannot afford for a single data center to go offline. They run highly available clusters spread out across multiple geographic locations.
Absolutely essential today.
But this requires incredibly careful architecture to avoid an absolute catastrophe if those sites lose contact with each other. Question 8. You are designing a highly available enterprise database cluster distributed evenly across 2 independent geographic locations. To prevent a split-brain scenario during an intersite communication failure, what is the best practice for deploying the tiebreaker component?
The correct answer is D.
Let's get into the architecture of a split brain and a tiebreaker.
Okay, so the document dictates that the tiebreaker must be situated in a third, completely independent location.
A third location, yes.
Yes, this third location must maintain its own autonomous network connectivity to both of the primary cluster sites. If the network link between the 2 primary sites fails, this third site provides an external independent quorum vote.
Okay.
This quorum vote safely determines which of the 2 primary sites gets to remain active.
But wait, why go through the massive expense and networking complexity of building out a completely separate third location? Why can't we just configure the primary production site to mathematically default to being the boss if the connection drops?
Because in a severed network scenario, both sides are essentially blind.
Blind.
Yeah, imagine the fiber optic cable connecting Site A in London and Site B in Paris is cut by a backhoe. Site A looks at the network and assumes Site B has burned to the ground.
Right.
But Site B looks at the exact same severed connection and assumes Site A has burned to the ground.
So they both think they were the sole survivor.
Exactly. And if they both default to becoming active and they both start accepting new database transactions independently from different customers, your data immediately diverges.
Oh, that bad.
That is a split brain. When the network connection is finally restored, the databases are hopelessly corrupted because they have completely different records for the same time period.
Right.
You can't easily merge them back together.
And the third site prevents that.
Yes. The independent third-party vote is a mathematical necessity to establish a quorum. If the link breaks, Site A asks the third site in Berlin, hey, can you see Site B?
And Berlin says,
yes, Site B is perfectly fine, you just lost your direct link. Berlin then casts the tie-breaking vote to keep Site A active and immediately pauses Site B. It is the only way to avoid catastrophic data corruption.
that is a critical safety mechanism. All right, now we're going to zoom all the way in from vast, multi-geographic cluster architecture back down to the internal fabric of a single compute chassis.
A big shift in scale.
Is. Question 9. In a composable infrastructure environment where compute modules connect through an integrated fabric, how is the internal networking bandwidth allocation optimized for diverse workloads?
The correct answer is A.
So how does this optimization work under the hood? We aren't moving physical cables, right?
No, no. The days of manually moving cables are over. In composable infrastructure, optimization is achieved by defining logical interconnect groups.
Logical interconnect groups.
Right. These groups apply software-defined network profiles directly to the modular hardware components. This allows administrators to define consistent network configurations and shift bandwidth allocations dynamically based purely on the workload's immediate requirements. It totally eliminates the need to repeatedly reconfigure the physical hardware fabric.
You know, this sounds a lot like a digital mixing board in a modern recording studio.
How so?
Well, 20 years ago, if a music producer wanted to route a microphone to a different effects rack, an engineer had to walk over, physically unplug a heavy cable from the wall, and rewire the patch bay by hand.
Yeah, totally manual.
Right. It took time, and humans make mistakes. But with a modern digital board, or in our case, composable infrastructure, you don't physically touch the hardware. You wire the massive integrated fabric exactly once. From then on, every single routing decision, every bandwidth change is just a software profile applied on the fly.
Yes. And to build on that, the operational impact of that shift is just staggering. Your mean time to provision a new environment drops from days or weeks of manual labor down to seconds of software automation. The physical infrastructure becomes completely fluid.
Amazing. Finally, we are going to take that concept of a fluid, software-defined fabric and expand it to try and solve one of the biggest, most expensive problems across the entire enterprise data silos. Question 10. A research facility struggles with data silos across various analytical tools and storage clusters located at the edge and central core. How does an enterprise data fabric solution resolve this specific architectural challenge?
The correct answer is C.
Let's break down the mechanics of this enterprise data fabric.
So the architectural material explains that an enterprise data fabric unifies all of those distributed, disparate storage environments into a single logical file system structure.
Okay, a single logical structure.
Yes. It creates a unified logical namespace across the edge, the core data center, and even the public cloud. The fundamental result is that authorized applications and AI tools can access all the data transparently and consistently without requiring the business to physically consolidate the information.
Let me clarify the physical reality of this. If I have a massive research facility generating petabytes of localized sensor data at the edge, data gravity tells me it is incredibly expensive and slow to move that data.
Extremely expensive.
So does this fabric mean I don't have to physically drag, copy, or duplicate all that edge data across the network into one monolithic central database?
No, you do not. That is the genius of the data fabric. The data physically remains exactly where it was generated and stored, whether that is on a ruggedized server in a remote desert or in a deep, cold archive in your central data center.
But the applications querying the data, they don't know it's scattered all over the world.
Exactly. The data fabric acts as a brilliant abstraction layer. It creates that unified logical namespace. To any data scientist or AI model querying the system, it looks and acts like one giant cohesive local drive.
That's wild.
Yeah, the fabric handles all the complex background routing to fetch what is needed. It completely shatters operational data silos without the massive network latency and astronomical cost of physically moving petabytes of data across the ocean.
We have just sequentially mapped the architecture of the HPE7-V01 exam, navigating everything from scaling block storage and isolating recovery vaults to software-defined networking and unifying enterprise data fabrics.